Good afternoon. My name is Karsten Plesser. I'm a principal here at Amazon Web Services, and today's talk is going to be about estimating your Graviton ROI for both improved price performance, but we'll also look beyond cost and look at sustainability. It's my great pleasure to also introduce my co-speaker today, Derek Frajancek. He is a senior performance engineer at Splunk, and he'll talk a lot to us about some of the lessons learned and the journey that Splunk took in migrating workloads to AWS Graviton. So a bit of context, today also completes 2 years for me in the San Francisco Bay Area. The last time before this pandemic was in fact at Sydney Summit that I presented to a live audience. So I'm so glad to be back up here on stage presenting to you. A bit about myself, I like to focus on next generation architecture. So over the last 12 months, I worked with Splunk on their move to Graviton. And one of the things I really like to focus on is enabling you to think about performance and performance optimization and what this can mean for your workloads and how, as an independent software vendor, you can use that as a differentiated advantage out there in the market. So what can you expect today? Well, first, we'll talk about a mental model, but we'll use Splunk's journey to back up and look at a lot of the lessons learned through the joint work that we've done. Splunk recently announced that they're moving their Splunk Cloud offering, a data-to-everything platform that's a SaaS offering, to AWS Graviton for enhanced performance for Splunk customers who choose AWS as their provider. And so we'll, in the next 60 minutes, look at setting the stage, defining learning objectives for you. We want this to be a practical talk, something that you can apply. And we'll then hone in on the storage optimized portfolio of Amazon EC2, which is one of the things that we'll talk a lot about in Derek's part of the presentation, which was one of the deciding factors for Splunk to make this move. I'll then develop a mental model to help you rationalize TCO and ROI decisions when it comes to moving to Graviton. Derek will help us recap some of the lessons learned from Splunk's journey to Graviton. And then we'll close it out with some additional resources that you can use for self-paced learning and study if you're doing this at this moment yourself. All right, so I'm going to get us started here. You are in the right session if I need to ask the question, why is this level 300, right? We're going to make a bunch of assumptions of where you are in your AWS Graviton journey. And most importantly, I am going to assume for a lot of the calculation examples that you are running storage-intensive workloads. I will also assume that you have completed at least the initial enablement of your software to have your software run on AWS Graviton instances. Now, I fully understand this may not be the case for all of you in the audience today. So I will provide resources and references later on throughout the talk if you're a bit earlier than that and you're still thinking about how to actually make your software run on the new Graviton instances. So for the purpose of today, however, I want to make sure that we clarify that we will focus on TCO and that we will assume that you've already completed test evaluation of your software on the AWS Graviton instances. So moving along here, at the end of the session, I want to define some of the learning objectives that I want you to walk away from today's session with. So first one, we'll talk a lot about identifying variables that drive performance of your workload. I'll give you a few examples and we'll talk about how, in Derek's part of the conversation, what those variables are that drive the next level of performance for your workload. We'll then look at picking the right migration path. So how do you go from a source instance to a target instance? And what is the logic and the system behind doing so? I'll stress and cannot stress enough the importance of running performance tests, because when you do TCO modeling only on a spreadsheet, you're bound to have or make assumptions. But we'll focus on performance testing as a way to use data to prove that these assumptions are correct and then to iteratively refine them. So ultimately, all of this mechanism and the system is to help you define and validate your TCO assumption if you are at the stage where you're deciding if you should cross the bridge and move your workloads to AWS Graviton. Before we do so, I want to take a moment to do a brief recap of storage-optimized instances in Amazon EC2 today. This will play an important role later on. So, as you know, Amazon EC2 offers the broadest and deepest set of compute instances in the cloud today. Our customers use this choice to run virtually any type of workload, and we offer compute-optimized, memory-optimized, general purpose, and also storage-optimized instances. Now, what's unique about storage-optimized instances is that they give you higher I/O, lower latency, and plenty of SSD storage if you need to run workloads that require large amounts of local storage. So, by way of example, many of our customers use the I family, which is the storage-optimized instance, to run workloads such as real-time databases, key value stores, or any workload that requires you to maintain a large cache of data locally close to your compute. So over the years, we made several upgrades to our storage portfolio, including the i3 instance back in 2013 and 2017, and then the i3 instance back in 2013. And over the last 12 months, we've been busy upgrading that portfolio to offer you better price performance by introducing a new Graviton storage optimized option. And so we'll talk a bit about what this option offers to you. We've also upgraded our Intel portfolio with i4i, which we announced at reInvent, and we'll look at some of the details in the following slides. So, using storage-optimized instances, what gets customers excited a lot about working or moving workloads to Amazon EC2, and in particular Graviton, is that improvement in price performance. And so over the last 6+ years, we've worked with Annapurna Labs to bring you innovation that drives price performance for your workloads. Now today, we'll really just focus on two aspects of this overall strategy, which is to look at Graviton and its impact on your workload on the compute side. But we'll also discuss the Nitro SSD benefits, which is a new storage tier that we launched at reInvent that gives you up to 60% lower I/O latencies. Now, there's of course plenty more work that we have done and innovations that we brought to you back at reInvent in 2021. However, we won't really have time to go into detail. I do or can, however, recommend that you look up the two talks given by both Ali Saidi and Arthur Petitpierre, who presented earlier today about aspects of the Nitro system, as well as a lot of the innovation work that we're bringing to you with Graviton 3. So Graviton 2 and price performance, up to 40% better price performance, gets many customers excited. But we needed one more aspect to bring you storage optimized instances. And so this is the Nitro SSD system, which we announced at AWS reInvent back in 2021. Nitro SSD is designed from the ground up to bring you better price performance with up to 60% lower I/O latency for storage optimized workloads in particular. We designed Nitro SSD, or we extended innovation with Nitro SSD not only to hardware, but also including innovations in terms of firmware and software. So for example, we tightly integrate Nitro SSD into our overall Nitro system, which powers our current generation instances to give you that better price performance. We've also worked on security. So Nitro SSD volumes on your storage optimized instances are encrypted with AES 256 ephemeral keys. So the data that you store on these instances and in these volumes is encrypted, it is secure and safe. So let's dive into each instance to give you a bit more detail about how these are positioned. And when we start talking about moving from an existing third generation instance type, the mental model of mapping the instance types will make a lot more sense as we proceed throughout the talk. IM4GN is first up here. IM4GN is really for workloads that require extra compute performance. So it gives you up to 40% better compute performance at up to 44% lower dollar per terabyte cost. Absolutely essential if you're running workloads that require large local volumes, up to 30 terabyte of local disk capacity on SSD using the AWS Nitro SSD volumes that I introduced before. These instances also provide enhanced networking up to 100 Gbps, which is very important if you run a data-intensive workload and something that Splunk uses when testing and using these instances in production. Now, the IM4GN instance type comes in 6 sizes. It is available today in major regions, including Ohio, Oregon, North Virginia, and Ireland. So you can try out these instances yourself by logging into the AWS console. The way our customers use these new instance types is for workloads such as relational databases, NoSQL key value stores, or data indexing search workloads where you need to really hold large amounts of data local so that you can result your search requests faster with very low latency, something that is absolutely crucial if you're running or if you're optimizing for end customer outcomes. Moving along, this is IS4GEN. Now, IS4GEN offers you the lowest dollar per terabyte of any instance in the Amazon EC2 portfolio. So it is great for workloads that need 30 terabyte of local storage at up to 15% lower dollar per terabyte cost over i3EN, which is our 3rd generation instance type that is storage optimized. It offers the same performance characteristics using the same Nitro SSD underneath as IM4GN. And it is a 50 Gbps network bandwidth for fast data access to services like S3. One of the things I always like to joke about is that the S in IS4GN really stands for Splunk. So the importance of your feedback is absolutely fundamental in helping us shape and develop these instances and ultimately bring them to market. We work backwards from your requirement, and the feedback that you provide to us is absolutely crucial in helping us decide whether or not a particular instance type does see the light of day. Again, our customers use IS4GN for workloads such as NoSQL databases, data streaming, or distributed file systems, or again, search workloads where you need to hold really large volumes or retain data for a long period of time, very close to your compute. All right, so price performance, up to 40% better price performance is one of the standout features of AWS Graviton. And so it gets customers excited of what they could be able to achieve. Now, if you're looking at price performance, then of course, I don't think there's any customer out there today that would design or optimize their systems for lower performance at higher cost. What you're really looking to achieve is to get to same or higher performance when making a migration and selecting a new instance type by also lowering your cost. So what's absolutely fundamental is that as you get started in selecting these instances and evaluating their use, to be clear about the migration objective or the optimization function that you do want to build. Now, the cost component, we're public with the pricing, at least the on-demand rates, on our Amazon EC2 pricing page. So you can work out what the instance pricing looks like. But price performance is more than just the cost of an instance. It also means understanding, and that's the extra work that you need to do, it's understanding how your workload performs on these new instance types so that you make sure that you deliver the same or higher performance outcome to your end customer. And so we'll talk a lot about how this is best done. So when I talk to customers about Graviton, then they're usually excited about hitting 40% better price performance. Now, some customers then ask what the kinds of micro benchmarks are that they should use when evaluating a particular instance type. Now, in almost all of these cases, I'm able to convince customers that micro benchmarks are never a good idea. So here's the reason why. Micro benchmarks evaluate an instance under artificial lab conditions. They never represent the real-world performance outcomes that your customers expect from your software. So my first recommendation when we start talking about performance optimization is that you work backward from outcomes that your customers are willing to pay for, something that differentiates your software offering from other software offerings out there in the market. So don't use micro benchmarks, but work backwards from outcomes like throughput or lower latency or completion or error rates. Customers are willing to pay to get faster search results, to get a more reliable and stable system, or to have a system that can process more units of work in the same unit of time. So define performance based on actual workload outcomes, and don't use micro benchmarks to test specific subcomponents of the system and get to outcomes that customers do not notice when they use your software. So establish your migration objective in terms of these customer outcomes, and then take the next step by looking at the specific variables in your workload that drive these outcomes. I like to think of these as the unique building blocks, adding an additional building block of which will get you to the next level of performance. And it's very important to figure out what that unit or that building block is. Now with Splunk today, we'll look at a CPU constrained workload. So adding an additional virtual core or vCPU is a way of measuring the performance optimization and mapping function. But your mileage may vary and your workload might be memory constrained, or it might be storage or disk capacity constrained. So it's important to figure out, and the way to think about this is adding one more of a given type, such as a vCPU or a gigabyte of storage or a gigabyte of memory. How material will that impact be on the end customer outcome? So when you start evaluating an instance type, we usually start off on a very high level, which is to compare the different instance sizes and the instance types in both the source and the destination family. In a moment, I will drop a scenario where we look at a 3rd generation x86 instance, and we map that to a 4th generation Graviton 2 instance. But most importantly, when you do these mappings, we often start at a level of 1-to-1. So if I pick virtual cores or vCPU as my bounding variable, and I do a 1-to-1 mapping, I'm bound to get higher performance because of all of the innovation work that we put into developing these instances. However, at the same time, because you get double the storage capacity on the new IM4GN instances, as an example, you're also paying more at an instance level. So you're paying for higher performance. So if your cost or if your optimization objective is to get to cost savings, then you need to look at some of the other optimization techniques that we've summarized here. So by way of example, in a scale down scenario, you're looking to reducing the number of vCPU on a single compute node. If you run a cluster and you pick an individual compute node, you're trying to have, for example, halve the size of the vCPU on that node. I will drop an example to make this a bit more clear in a moment. Now, that's not the only mapping technique that you can use or the only scaling or optimization function you can use. You can also look in cases where you can't drop a size of a node or instance type. You can also do a scale in, which means looking at a cluster level, you can run a denser cluster with less number of nodes. Now, of course, in reality, what we see most customers do is that they use a combination of these different techniques. So we've seen examples where customers both scale down and run a denser cluster. As long as that gets you to the desired performance outcome, any combination of these techniques work. So let's put this into a specific example to help you develop that mental model of how to think about TCO when you do these instance type migrations. So on the one side, we have a 3rd generation x86 instance. In this example, I've picked an i3, so a storage optimized instance, 3rd generation, 8x large. On the other side, which is my destination instance, I'm looking at a 4th generation Graviton 2 instance. In this case, I'm doing a 1-to-1 mapping based on my performance variable vCPU So in both instances, I have a 32 vCPU count, both in the source node as well as in the destination node. If I draw up that comparison this way, I also quickly start realizing that in terms of the shape of these two instances, with the 4th generation storage instances, we change the ratios. So by way of example, I get half the memory density per vCPU core than I had in the 3rd generation instance. However, I get a significantly higher storage density, so double the storage density compared to 3rd generation at a lower dollar per terabyte cost. So drawing up your analysis in this way helps you to make sure that you have a good starting point. So great. I mentioned earlier that at an instance level, this may not lead to material cost savings. So how do you actually start thinking about developing cost savings? So the key to doing these mappings and understanding your ultimate destination instance type is that you work backwards from the customer outcomes that we talked about, the performance outcomes, and that you gather data via performance testing. Now, we won't have sufficient time to go into a lot of detail of how you build a performance engineering discipline in your teams and your company. Companies like Splunk run a performance engineering team and have a systematic and data-driven approach to evaluating these instances against defined performance outcomes. However, I do have a link up here. If you are interested in this topic and you think your company has not yet built this discipline, we do have a white paper specific to software as a service companies that are interested in that performance testing method and how to go and start your performance testing effort. One of the key points, of course, is to work backwards from clear workload metrics, to repeat your testing, and to also test under real-world conditions. So don't use lab conditions, but try and test against real-world assumptions. And Derek will talk to us a lot more about what he did as part of the evaluation that Splunk conducted. So let's move along. One of the key outcomes of your performance testing exercise is that you will get a more granular understanding of your scaling factor. So in my hypothetical example, which is only part of developing a mental model, let's say I figured out through performance testing that I'm able to scale down my vCPU count in the destination instance by 50%. So I'm going from a 3rd generation processor with 32 vCPU to a 4th generation with 16 vCPU, where those 16 vCPU pick up the extra slack because of the performance improvements that we made in Graviton 2. Again, I need to watch out for my memory density because as I have the vCPU count, I also have the memory density, the memory available on that compute node. So through performance testing, I do want to make sure that I still hit the same performance outcomes that I, for example, latency, that I was able to achieve in my 3rd generation instance in that new instance type as well. Now, if you're memory constrained, then of course, you do have to evaluate and take that into consideration. However, I get the same storage per node, the actual capacity, that's the same, about the same, at significantly lower dollar per terabyte cost. So I'm starting to see cost savings now. So the whole point of this is developing the scaling factor that helps you understand how you move from a source to a destination type using that bounding variable of vCPU and how much of that ratio you can afford. Can you go down 33%? Can you go down by a third? So developing that scaling factor takes time. And so this process repeats until any new unit of testing on that destination cluster only yields diminishing returns. So in my example here, I have a 2-to-1 scaling factor. I can take 2 3rd generation x86 vCPU, and I'm going to replace this in my destination cluster with a single 4th generation vCPU. And so I can now run my numbers in estimating the size of my destination cluster and the instance types in that IM4GN instance family that I'm able to pick. All right, so let's put this all together before we move on and then talk about lessons learned from Splunk's journey. So I want to leave us with a mental model or a calculation formula And the way to think about TCO is simply the difference between the costs of your source cluster to the destination cluster. The cost, of course, is simply the total number of vCPU that you originally had times unit cost, so dollar per vCPU, and then comparing that to the total vCPU and unit cost in a destination cluster. To make this a bit more tangible, here's an example of how to draw up your cost savings and present them. So in this example, again, I go back to my original source instance type, my assumption using an i3 8x large. I have a cluster size of 3 nodes, and I have the 33 vCPU per node count that I introduced earlier. I've also drawn up my DRAM per node, so the memory density, storage density, and other metrics here. I can now run 2 scenarios, a conservative and an optimistic, depending on how much safety buffer I really want to build into my calculation. So for example, knowing or based on my performance testing, I know I can drop a size going to an IM4GN 4x large, which has half the number of vCPU than my source type. I can now make an assumption that I need to increase the number of nodes per cluster to have a safety buffer of only dropping vCPU footprint by 33%, which yields a total cost saving of 22. These slides are going to be available after the session today, so you can work the math yourself. But this is a great way to explore the boundaries of what's possible and how to calculate and justify the TCO calculations that you're making. In an optimistic scenario, I can go the full 50%. So I can halve my vCPU. I can halve my vCPU footprint, and that takes me up to 42% cost savings. So I drop a size, go to an IM4GN 4x large, but I only run 3 nodes in this cluster, giving me the same performance output than in my original 3rd generation x86 cluster. So that's absolutely awesome if you're a financial officer or you're working on cloud finance as a way to justify the investments to then move these clusters over to Graviton 3, or 2 in this case. So that's a lot of mental model, and it sounds a little abstract. In order to make this more tangible and hopefully also help you relate to some of those lessons learned, I want to invite Derek up here to come and talk to us about the journey that Splunk made and some of the lessons learned that Splunk made along the way. So Derek, come and join us up here.
Thank you, Karsten. Hey everyone, my name is Derek Ferenchuk. I am a senior performance engineer at Splunk. I help to lead the charge converting Splunk's software as a service offering from Intel to Graviton. And I'm here today to talk to you a little bit about the journey we took, the lessons we learned, and hopefully some of those lessons will be applicable to you as well. With Karsten's mental model in mind, we need to first start and understand our own workload profile and understand why does Splunk use storage optimized instances in the first place before we get into the nuances of these Graviton subflavors and these Intel and what's an educated decision that we can make between the two. Splunk, for those of you who are not aware of what we do, is a data-to-everything platform that takes machine data, logs of any format, any source, whether it's structured or unstructured. We run some indexing and computation on top of that data and make it searchable by the end customer so that they can derive value and ask questions out of their data. As you can imagine, in the world of big data, this results in a very high level of I/O load that we impose on our disk systems. So bandwidth and latency are 2 areas that we care about quite a bit. The local SSD offering that AWS offers is quite performant and serves us well in this regard. And the Nitro SSDs that Karsten mentioned a little bit earlier are a very welcome enhancement on top of that. With that said, Splunk cares about disk storage capacity just as much as disk performance. Storage capacity meaning how much storage is available per instance on my machine. The reason is that, for context, Splunk stores a lot of our customers' data on the cloud in a disaster recovery capable, cost-optimized storage backend, for example, AWS S3. However, to get those fast searches that use all that bandwidth and latency that we're talking about, we need an adequate amount of local capacity on the local disks to handle the working set of data that is being searched over by the customer, similar to a cache. I know not everyone works in the same field, so I wanted to give a quick analogy of how RAM acts as a cache for the disk of your laptop or your phone. So I'm going to try to wake you folks up a little bit. I know it's the end of a very long day. Does anyone here like to have a lot of tabs open at once? Or maybe you don't like it, but you have a tendency to leave a lot of tabs open? See a few hands. I'm not alone here in this proclivity of mine. Those of you who raise your hand with me might be familiar with this scenario where you have a lot of tabs, a lot of applications all running at once, and it almost feels like you hit a wall and things really slow down and become almost unresponsive. And you might ask why this is. Well, one possible explanation is that the working set of data that you're trying to operate on concurrently with all these tabs, all these applications is insufficient for the amount of RAM or the amount of memory capacity that your device has available. Therefore, your operating system has to take these pages of virtual memory and page them back and forth in and out of disk. The issue with this is that disk accesses are orders of magnitude slower than accessing local memory. Therefore, you have this very slow access that gets propagated back through the system and ends up impacting the end user experience, feeling slow, unresponsive, and overall ugly. So that is a pretty similar scenario to what happens with Splunk if you don't have enough disk capacity. So we combine our need of disk performance and disk capacity, and the storage optimized instances that AWS offers are the optimal instance type that really serves our need. With that said, we also use a fair bit of network and CPU usage as well. We're streaming a lot of data back and forth and running rather compute-intensive calculations on top of this data. Generally, what we find, given our workload profile and our software as a service offering fleet, we often find that we are CPU limited once we have a strong enough disk to service the workload that we have. So when Karsten came to us and talked about these Graviton-powered storage optimized instances, we were very excited because this is a cost-optimized, efficient way to attack our #1 bottleneck in our fleet today. So that's kind of the background for why are we talking about these instance types? Why does Splunk use them? Well, let's talk about our journey about how we actually evaluated Graviton and whether it was a proper fit for us. As Karsten mentioned earlier, you have a couple different options available. You could horizontally scale in or vertically scale down. For us, there were a couple guardrails or limiting factors that prevented how much we could go in either direction. I'm going to call them out in case they might be a little relevant for you as well. For the horizontally scaling inside, there was only so far that we could truly scale in because Splunk is a parallel search execution platform. So if you don't have enough parallel machines running on a given query, you might have the end result slow down, and that's essentially unacceptable. Customers are paying a large level of money for the fast performance that Splunk offers. So if we can't horizontally scale in too far, what about we vertically scale down? An issue with that is that in our testing, the Graviton machines were not quite twice as strong as the Intel machines. So we couldn't necessarily go down one notch, for example, from an Intel 8XL to a Graviton 4XL. Another thing that Karsten mentioned earlier was that the ratios of CPU to memory are slightly different with these new instance types. On Intel, it was approximately 1 vCPU to 8 gigabytes of memory, but with Graviton, it's anywhere from 1 to 4 or 1 to 6. Therefore, if you're also taking that lower ratio and you're scaling it down, memory may go from something that may not be an issue for you to all of a sudden becoming a major bottleneck that you and your team have to worry about. What worked for Splunk was a combination of scaling down and scaling out to attack those two different scenarios. With that in mind, we need something to actually perform our apples-to-apples testing to compare Intel versus Graviton and see what makes the most sense for you. In that regard, we highly recommend using a customer representative benchmark to translate what all these enhancements mean for you. AWS, they created the hardware, they tuned it the best that they could, but this is for the general use case. Everyone sitting here has a different load profile, a different use case, and you have to figure out what your use case can derive out of this hardware. How can you do that, you might ask? Well, you could look at the distribution of workload profile, figure out what key metrics matter the most to you and start measuring them. Look at the resource usage. We could go on and on and on, and that's why we have the white paper linked on this section at the end of the slide deck that will be shared out later. And the reason why you might want to do this, even if you have already done this years ago, is that there's often a lot of drift and the assumptions and beliefs that folks at your company might believe your workload profile looks like and where you're bottlenecked versus the difference in reality. Splunk had this as well. The issue is that the software and the hardware industries are moving so fast that these assumptions that we make and hold fixed over the course of time often no longer hold true due to the drift of the moving industry. So I highly recommend, if you haven't recently reevaluated your workload and looked at your fleet, to stop, do so, and get a true representative workload, because I promise it will help minimize the amount of escalations you encounter and maximize the amount of savings that you're able to realize from this endeavor. Now that we know, okay, we have something that we can actually test with, let's get started. For background, back when I was studying in university, the university I was at helped invent the RISC-V instruction set. So I was already relatively familiar with ARM, and when I went to Splunk, I noticed this opportunity to evaluate this cutting-edge hardware on our workload. So me and two buddies, two fellow engineers, took a single hackathon to hack together Splunk on ARM, fix all the dependencies to work enough so that we could get some initial testing to figure out how exciting, how realistic are these results for us. And that's a key thing that I want to get away. You don't have to wait till next year. You don't have to wait till you have a whole team of engineers for this. This is something feasibly that if you wanted to, you could get started with next week and potentially finish your initial evaluation next week. And by doing so, you get that initial proof of concept that helps you go to internal stakeholders and make that educated decision of, is this worth it for us? Is it worth it to put X amount of resources? Should we put more? Should we put less? Do we put this on the back burner, or is this a must-do now? It all takes a relatively simple amount of energy to get started with, and once you get over that hump, you'll actually be surprised by how easy it is, especially in recent years, as the ARM and Graviton ecosystem have really been accelerating. Once we took these initial testing results, the potential savings were rather large for us, so we started investing some resources and continually optimizing our software for the key metrics that we care about. At Splunk, similar to what Carsten mentioned, we care about search response time, search completion rate, and other factors among those. There are a lot of areas that you can use to really take advantage and tune your performance for Graviton specifically over Intel. There's atomic instructions, there's Graviton's equivalent of vectorized instructions. There's a lot that you can really fine tune and identify as bottlenecks after you move over, once you've made the initial decision of whether it's worth it or not for you. After we kind of went through this cycle for a while and we did the period of refining and evaluating, we ended up coming up with the final apples-to-apples comparison between Graviton and Intel. And that allowed us to make a granular customer level, workload level analysis of which workloads were best fit on the powerful CPU of the IM4GN family, which workloads took best advantage of the dense storage of the IS4GEN family, and which workloads might be better left on Intel to take advantage of that memory ratio that we were talking about earlier. Anecdotally, we found for us that customers that had very heavy searches, a lot of regular expressions, and very computationally and heavy work, they were best fit on the IM4GN and was substantially better over the i3 Intel equivalent. On the IS4GEN side, that was best for customers that searched over a relatively large amount of data, had that large working set, as we were talking about earlier, without too heavy computation on that data. So that was kind of our end-to-end of how we started, how we evaluated it, and what we ended up with. That brings us to some lessons learned, some gotchas that hit us, and hopefully I can share with you that you can avoid when you go down this road. First off, I know the numbers are exciting. That's why a lot of us are here today. What Carsten shared is great, but you don't want to get caught staring down this Excel spreadsheet that you've been working on for weeks, overanalyzing these ratios and trying to figure out this theoretical migration that you're going to do with your workloads. The issue is that there are a lot of nuances and truths that don't come out from your assumptions. They only come out when you start testing. For example, one that hit us was the notion of an effective CPU strength to memory ratio. This is something that we hadn't really considered before. We thought about, okay, the ratio of vCPU to memory is less, but what we did not think about was that if there's stronger per vCPU power, then you can do more work per vCPU. Maybe you might need more memory per vCPU to handle that extra workload. Okay, well now we have an even more combining and compounding factor on memory is starting to become a little sparse, if you can imagine. So that was a big gotcha that we did not understand when we were making the spreadsheets, and it hit us immediately when we started testing. And there were a lot of spreadsheets that were made at Splunk when we first went down this road, and I can guarantee you that 99–100% of them were thrown away relatively quickly after we started testing, just because we could not model all of the unknowns that we encountered once we started testing. Another gotcha was that we personally had memory issues with our memory allocator, JE-malloc. We had this long-time stable version of JE-malloc that we ran on Intel, and it had served us well for many years. The issue is that when we hacked ARM together, a Splunk on ARM, we just used the ARM equivalent of the same version of our libraries and dependencies rather than kind of upgrading everything at once. We didn't want to deal with the potential issues that could cause. Well, on Graviton, we saw a 10x increase in memory usage over Intel, which would have been a deal breaker for us, especially considering all of the relatively compounding memory factors that we have talked about so far. So we did our heap dumps, flame graphs, deep dives, trying to figure out where is all this memory being used? And we went to Karsten and our partners on the AWS side because the solution architects kind of managed the whole Graviton ecosystem with all the different vendors involved. They recommended that we upgrade to the latest version of JE-malloc that had a lot of ARM and Graviton specific optimizations that were not made back when this original old version of JE-malloc was created. Upgrading did help in one regard. It also gave us another serious issue, which was a monotonic increase in memory usage. In other words, the process never released the memory to the operating system. Another deal breaker for us. To keep a long story short, what we found was that using the new version of JE-malloc, we switched from a ratio-based memory deallocation algorithm to a time-based decay memory deallocation algorithm. And this gave us some issues, but we were able to fix it with an idle background thread, and we actually got better memory usage in the end off of Graviton over Intel, which was a nice cathartic finish to this stressful endeavor. What I wanted to call out from that is we would never have caught it with spreadsheet analysis. This was only an issue that we were able to encounter by getting dirty and really testing those customer realistic workloads that we were talking about before. Another silver lining that I want to call out is that we really refined our usage of atomic instructions. The ability to take your performance critical areas and optimize them specifically for Graviton with atomics and vectorized instructions can really further increase your performance or your savings that you get out of it. So I recommend that if you have a very strong opportunity on Graviton, to look at your performance critical areas, see where you can further refine them to be specifically more powerful on Graviton, and really make the most out of the tools available to you. Which brings me to my final bullet point here. Upgrade your tools. Upgrade your operating system, upgrade your libraries, upgrade your dependencies. I know there's a lot of pushback, there's a lot of inertia at companies around this, but the Graviton ecosystem was relatively nascent only a few years ago, and it has really rapidly started to evolve. And there are a lot of optimizations that have gone in on your libraries and dependencies in the past few years that will completely change your performance profile if you migrate. That is seen, for example, in JE-malloc, among many other tools. Another example is if you're on Ubuntu and you're on 20.04 or later, and you migrate from GCC 7 to 10 for compiling your code, you can see an additional 15% performance increase over everything that we've already talked about so far. There's also, for another goodie, large system extensions. These are atomics that are specifically designed to be highly performant on synchronization and locks. So if you have highly concurrent, highly parallel workloads, this can be another big area where you can get a lot of performance improvements. With that said, there's a lot of areas that you might feel like this is overwhelming. You might get stuck. There might be an issue where there's a library that's not available on ARM or a dependency. Don't panic. Reach out to your solution architects at Amazon. They're happy to help you. They're happy to partner and figure out what they can do. With that said, I'd like to hand it back to Karsten.
Thank you, Derek. That was awesome. It is so important to hear from customers how they're utilizing our instances. We do a lot of these optimizations at the hardware level, but we really want you to utilize these instances and get a benefit from using them by running faster systems or more cost optimized systems. Now, we focused a lot on cost and performance benefits of making the move to Graviton. But looking beyond cost, there is a lot more that you can do. At Amazon Web Services and Amazon more broadly, we do a lot to invest in sustainability. Running workloads on Amazon Web Services is up to 88% more carbon efficient than running the same workload in your own internal data center. Now, on top of that, we have pledged to make or switch our operations to 100% renewable energy by 2025. Now, combine all of these data points with the reduction in vCPU footprint, the denser clusters that you're able to run by switching to Graviton, and then consider some of the results of a recent study that Graviton 2 offers up to 3.5x better performance per watt. Then you're not only just saving cost, but you're also making a contribution to bring about a greener and more carbon efficient future. In order to help you with that journey, we've done a few things. So number one, we released more recently at AWS re:Invent 2021 our new sustainability pillar, which is part of the AWS well-architected framework. So this brings together a set of best practices that helps you think about building, designing, and deploying sustainable and carbon-efficient workloads. On top of that, we announced the Carbon Footprint tool, which allows you to track, measure, and forecast carbon emissions from your AWS usage. The Carbon Footprint tool is available today if you log into the AWS Billing Console. And you can use that to understand how your usage of AWS contributes to carbon emissions. Now, this is of course useful if you are designing sustainable architectures and you're thinking about sustainability as an outcome of architecture and design. However, we also find that your customers are starting to think a lot more about sustainability and carbon impact. So next time you get a data request from one of your customers, think back to the tooling that is now available on the platform, as well as the architecture frameworks when you answer that request. So come and help us make the world a little greener, one workload at a time. So some bonus considerations, taking us beyond just this initial stage of TCO and cost modeling. But once you are past this point of crossing the bridge in terms of TCO, there's a couple of things I want to call out. Opportunities to start working with your AWS account team. Number one, go and talk to your account team and your enterprise support team about your rollout plan for the primary regions and availability zones. Think about capacity reservation models such as the ODCR, or on-demand capacity reservation model, if you're migrating vCPUs or instances at scale. This might also be the time to consider support coverage through our enterprise support team, including having a TAM assigned to you and work with you through that capacity planning and the delivery of that capacity into your account if you're migrating significant numbers of instances. And then ultimately, think through the purchasing options as you transition from one fleet and architecture to another, how your purchasing strategy needs to change to support flexible instance families through examples such as compute savings plans. So I want to end on some notes on where you can turn to for help. And I will also leave up some resources for you to study and learn. A lot of the content that we presented today is available to you either as white papers which talk about the mental model, or in terms of lab exercises and workshops that you can run in your own account to test and try some of the concepts that we talked today about. So number one, reach out to your AWS account team as you do this modeling so that you get the right support and the right insights and the right guidance when you do this exercise. Know that you are the center of our attention and your AWS account team is here to support you. Number two, check out the AWS Graviton Getting Started Guide. This is a great source of information when you're trying to understand how to build, test, and optimize your software on these new Graviton instances. So it includes up-to-date coverage of operating system support, software upgrades, the support or specific guidance for popular programming languages, including Java, Golang, .NET, C, and C++. It also goes into some detail in terms of performance, optimization, and measurement, as well as the compiler settings you can apply when you're building your software for a compiled language like C, C++. Another great resource if you're starting to think about performance engineering and performance testing and how to run this effort on Graviton is our new AWS Graviton performance testing white paper. I'll bring up the link in a moment, but this really talks about how to define critical success criteria for your performance testing initiative, how to then design an experiment, how to run iterative test runs, gather performance data about specific outcomes, and how to instrument your workloads so that you're getting actionable performance data out of these test runs. Now, if you want to hear from other customers about how they're working and making that switch to Graviton, come and join us for an upcoming AWS Graviton Peer Connect. This is a roundtable that we've run in the SF San Francisco Bay Area more recently, which brings together software companies and cloud companies in the Bay Area to come and join us for a conversation about lessons learned, best practices, and an opportunity for you to connect with our peers. This is an invite-only event, and the next one's coming up toward the end of Q2. If this sounds interesting, please approach me either on LinkedIn or later on in the expo hall, or reach out to your AWS account manager in terms of signing up. So I'll leave this up for a moment. If you haven't already, take a screenshot or a photo. So the AWS Graviton Getting Started Guide, you can Google this, is a guide that's available to you on GitHub. It has a wealth of resources to help you get started if you're just before that stage of estimating your TCO. Now, our migrations white paper is a white paper that I wrote in response to a lot of the requests that I heard from independent software vendors about how to think planning their migration to AWS Graviton. And so it provides a set of checklists to help you both plan, resource, and then deliver your project in terms of a lot of the best practices that we spoke about, such as making upgrades to your software before you make the move. I also have the performance white paper up here. This is a white paper that had input from a lot of independent software vendors like yourselves today. And it focuses on how to build an efficient performance engineering discipline in your teams and how to run test runs so that you get that performance data that you need in order to build your scaling factor. And then ultimately drive your TCO evaluation of Graviton and deciding whether a particular Graviton instance type makes the cut. I also want to call out an opportunity to promote Graviton-compatible software through our Graviton Service Ready program, which recently launched. Now, this is a great opportunity if you want to promote that your software works on Graviton and want to work through our AWS Partner Network or the AWS Marketplace to advertise your Graviton support to customers on the AWS platform. So this is really important if you distribute software, for example, through the AWS Marketplace, or you have a SaaS offering that customers can find and select on the Marketplace. Now, if you're looking for more advice and more training, our training and certification teams are here to support you, either in building skills, cloud skills, be they on Graviton or other services. So we have a program in digital courses that you can subscribe to. Or if you want to certify your teams or individuals in their cloud expertise, then we do have a full AWS certification program that increases in complexity over time. At the associate level, looking at fundamental cloud skills, and you go up to a professional or specialty certification as you proceed through that journey. So with this, I'd like to thank all of you for your attendance today, for your interest in this topic. I'd like to thank Derek, who's been an awesome co-speaker, to really help us think in practical terms what it means to make that switch and cross the bridge in terms of TCO, moving to Graviton, how to justify this case internally with your teams, and then how to go about making that move to AWS Graviton in production. If there are any questions at this point, today, unfortunately, we can't have a live Q&A, I'd encourage you to either send us a note on LinkedIn or to meet us out there at the entrance to Expo. We'll hang around for some more time. So if you do have questions, please approach us and don't hesitate. This session will be recorded. So if you want to get access to the slides, there will be a PDF version that you will have access to at the end of today. And the session itself will also be available after some time. So if you do want to go back and listen to a particular point that we raised today or a particular discussion item, then that recording will be available. So Derek, we have a few minutes left. So I thought we could use that opportunity to do an open Q&A on some of the common or most frequently asked questions that customers typically ask us when we have conversations about Graviton. And so Derek, earlier on in your talk, you kind of set the context saying that a lot of this move originated from a simple hackathon, and that this was really the starting point for this broader evaluation of Graviton. Now, how much work is it really?
Yeah, it's going to vary, of course, based off of how complicated your system is, how many libraries and dependencies you are. But it's, I guess the short answer, way simpler than a lot of people probably think. It sounds very monumental, moving to a whole different hardware architecture. But in reality, a lot of the tools that folks are already using today have ARM equivalents, relatively easily to support. And then once you go through the process of compiling everything, whether you're using Docker files, CI/CD, whatever, it actually comes out to be a relatively reasonable process. And you use whatever dev platform process you got, and you can then get your hands dirty, start testing initially. And of course, the full verification and whatever suite of workload you want to run through may take longer. But the time to value or the time to notion of potential value of this hardware is rather quick, in my perspective.
Awesome. Another question that we often get is, all right, I hit this particular bottleneck. How do I get help? So you referred to this earlier with this memory management issue. How were you thinking about this in your own project? I'll talk a little bit about what AWS can do to support.
Yeah, so as a performance engineer, this is my job to take bottlenecks like this, and there's a lot of resources out there that can help you understand what does it mean to take a CPU profile? How do I maybe convert it into a flame graph? How can I try to take a heap dump? But there's a lot of technical complexity that can really balloon here, and you may not be familiar with the details of a certain area, or you might not quite understand what's going on. Thankfully, Karsten and his coworkers are rather good at what they do. And what we noticed is that if we ever got stuck on something, we would reach out to Karsten and Ali, and they would be able to help walk us through, or potentially help even reach out to the vendor to help initiate a conversation for us to work together on figuring out what was going on.
Awesome, yeah.
Which actually,
thanks for that very kind comment about.
I only speak the truth. He did not pay me anything. My pockets are empty. But that brings me to a question as a user who converted their workload. What if I get stuck? And in this process, you're telling me it's going to be relatively simple to get started. But what if I have a dependency or a library that doesn't have ARM support? What can I do?
Yeah, that's an awesome question. Now, one of the things that I'd like to stress is you, of course, know your workload best. You know what matters and what libraries or dependencies you have. Now, we work actively with the software ecosystem to make sure that the choice that's available on the hardware side and the instance side is also available to you in the software ecosystem. So we often make upstream contributions to open source projects. We actively work with the community in helping them certify their projects on Graviton so that when next time you consider a particular open source project, you get an up-to-date build in a binary that you can use for your workload. So the Graviton Getting Started Guide has a list of the current supported libraries. Now, if there's a specific library that you find that isn't supported or doesn't have an up-to-date build, or you notice performance issue on a particular instance type, by all means, please let us know. We often work with project owners or the custodians of these projects to help them provide you with an upgraded build. This applies both to the open source ecosystem and community, but we also have mechanisms to help you when you talk, when it comes to commercial software. So I mentioned Amazon Partner Network before. Many of the dependencies and software tools that you use and the software agents that you use for instrumentation, as an example, these companies are part of our APN partner network. And so if you find an instance of a particular software agent not running on a particular Graviton instance, again, do let us know, and we can take it up with our partners. And we have processes and mechanisms in place to have those conversations on your behalf if you find that you're not making progress. In fact, one of the starting points of our conversation with Splunk was around the Splunk, lightweight forwarders that customers deploy into their ingest architecture for data collection, and getting that built and released to customers for Graviton instances. So as an example of how you can both work with us on moving workloads to Graviton, but also getting your software certified and distributed to end customers via the Amazon Partner Network.
Thank you, Karsten. As you can see, we clearly have a lot to say, but I believe we're at time for the day.
We are at time. So thank you so much.
Thank you.